Hi, welcome back to Lesson 2 in Unit 3 of Data Structures and Algorithms. This unit is all about binary trees. In our last lesson, we had a brief introduction to what graphs are, which we'll study a lot more in a later unit, and we looked specifically at some of the vocabulary and how to make binary trees. So, by way of review, and to get us warmed up and ready to code, we talked about a binary tree keeping things in order being a binary tree that keeps things in order being a binary search tree. So I want to look at making a binary search tree, or at least beginning to make one, for integers. Or simply, we can just say ints, okay? So let's say I had this tree here, and I'll make it a good binary search tree here. 5, let's say 3, 4, 1, and 7. Well, we know that these things here on the graph are called nodes, so we probably need a node class. But what does each node have? Well, each node will have some data, right? That we're going to just leave as an int. And it has a reference. Each node has a reference, just like a linked list. A binary tree is a lot like a linked list, a reference that points to a node. And we have a left child and a right child. So we're going to have a reference to a node that I'll call left, and a node that I'll call right. And we could call it's really right child and left child. Originally, though, they're going to be null. Okay, so let's go right into starting to do this. We need to make each node have a left and a right. So I'm going to make a new class called, oh, what are we going to call it? Maybe binary tree, or how about binary int tree? It's really a binary search tree, to be more specific. All right, so I'll just get rid of all that, and we'll say public class binary int tree. And we need to make a nested class called node. And we discussed that this time we want it to have data. We want it to have a reference to a node called left and reference to a node called right. Let's make a constructor. The only thing I want my constructor to take in, though, is the data. And initially, whenever you add a new leaf to the binary tree, the left and right children will be left null. And of course, they're already defaulted to null, but I'll just go ahead and make it explicit. All right, so how are we going to add to our binary tree? Well, we need to have a reference to get started. On our linked list, you'll recall that when we had a singly linked list, we started with a single reference to first. Well, for us, remember what this node is called? This node is called the root. So we are going to reference simply the root. Let's go ahead and do that. So our binary int tree class keeps just a reference to the root. And when you create the binary tree by calling the constructor, root simply is null. So let's talk about adding to the binary tree. So let's call this public. Let's see here. Now we have to make a decision. Are we going to allow repeat items in our binary tree? A lot of times you don't. Other times you could have the repeat items just kind of slide to the left. Let's go ahead and allow repeat items. So in that regard, we don't need to say Boolean because every time you're going to be able to add. Sometimes you have a Boolean, and if you don't allow repeat items, you would return false if you didn't actually add something to the tree. So we're going to say public void, let's say add. Okay? Add or offer. Sometimes people say offer the tree, and we're going to be adding int data. All right. Well, so we have a few different situations. If we have no tree at all, so let's go back in time here. So if we have no tree at all, then root must be pointing to null. So that's that's the simplest situation. So if our root reference is pointing to null, then we just simply need to make that reference. We just need to make that reference into our new node, because now we have a root. And that's what we're going to do. So here we go. If root is equal to null, remember, we use equals with objects when we want to see if it's null. But if you're trying to see if like the data from it is, usually, remember, most of the times you compare objects with dot equals. But when you're trying to see if it's null, you just say equals null. All right, so if the root is equal to null, then let's go ahead and add our data. So I'll say node in equals new node, and I will assign root a pointer to that node. Remember, in is a reference to the node somewhere in the memory, so we just say root, get that reference as well. So now we have a root to our tree, and we're done. So we could just say return, or we can continuously use else and else ifs. Yes, I'm returning, and I'm not returning anything. Perfectly allowed to just say return. I'll probably handle it with else ifs, though, so I don't have to say return, but we can. So else. All right, well, in this situation, we know that our root is not null. So what we're going to do is we are going to, let me go back to what I had before. So let's say we're trying to add, I don't know, the number 2. Okay? Well, what we're going to do is we're going to look and see, is this, when we're trying to add the number 2, we look at this, we start at the root, and we're going to look and see, and we're going to say, okay, is this node data bigger or less than the data I'm adding? Well, 2 is less than 5, so what we're going to do is we're going to travel to the left by taking the root's left node. And then we'll look at this 2 and we'll say, okay, well, 2 is less than this 3, so I'm going to travel here. And then 2 is greater, so I'm going to travel here. But I ended up null. So since I've reached a null, then I will add it there. Okay? All right, so we need to use a loop, and I actually am going to use that return feature to really help me. What I'm going to do is I'm going to loop indefinitely. I'm going to say while true. So this is going to loop indefinitely because true is always true. Well, I'll start here with let me make this current node. So I'll say node current. We're going to start with a current node pointing to the root. Okay, and I will say if current, I'll say data is less than current.data, then we need to slide left. So here's how we're going to slide left. We'll say current equals current.left. All right, well, let's imagine that we just did that. So I'm going to do a different tree to look at right quick. We'll say we have like a root of like an 8, and we're trying to add maybe there's a 9 over here. We're trying to add a 4. Well, we just slid to the left, right? We just slid to the left, and it turns out that we're at null. Well, then what does that mean? That means we found the place to add it, because we found a place where it belongs, and there's nothing there already. So we're going to do that. We're going to slide left, and then we're going to say, now we're going to say if current equals, oh, you know what? I have done goofed. Sorry, I have done goofed. I need to erase this. I don't want to move yet. I want to say if current dot left is equal to null. That means I need to move left, but it's null. Then I need to attach that. So then I'll say current dot left equals new node with the data I'm adding. Okay? So first I'm going to look and see if it's available. So if it's in this situation here, we had null, right? Which I'll just show as blank. So I'm trying to add, remember I was trying to add the number 4, and I say, okay, here's current. Current is pointing right here at 8, and I say, okay, 8 is current.data, which is 8. 8 is more than the data I'm trying to add, so I need to go left. So first I'm going to say, hey, do you have anything to your left? Because if you don't, I'd like to put a 4 there. All right. Well, let's say you did have something left, like a 6. Well, in that case, we know we need to move left, but it's not open for us to put it. So we'll say else current equals current.left, right? Well, what should we have done after we place the data? Well, after we place the data, we're done. And remember, the only way out of this loop is to return out of it since it's infinite. So we're just going to say return. So if we found the place to put it, great. You're done. Return. Get out of this method, right? Otherwise, go ahead and slide left. All right, what else could we do? Well, we could say else. That means that we were going to allow duplicates, but we're going to let duplicates slide to the left. So I'll say less than or equal to. So else we need to go right. And then we're going to say if current.right is equal to null, hurrah, we found the place to add it. Current.right needs to now reference our new node data. And then we return. Else, we need to move right. Okay. And that is pretty much it. All right. I think we've got it. We've got a good start on this, so let's compile it and we'll see what we can do. So I'm going to make a new binary tree. Okay. Put it on my workbench here. Let's add the number 7. Okay, great. Let's add the number 4. Let's add the number 6. And let's add the number, oops, I don't want to inspect yet. Let's add the number 9. Okay, so when I inspect it, let's see here. We have private int data, 7. Okay, because that's my root. I've got a reference to left. I've got a reference to right. Let's inspect the reference to right. The reference to right goes to 9. Okay, good. The reference to left goes to 4, who has a left node that's null and a right node that's 6. All right, well, let's pretend that we were going to try and find 6. So I'm going to find 6. How would I find it? Well, I would inspect the root. And I would say, okay, 6 is less than 7, so I need to go left. So I would go to the left. And then I'd say, well, 6 is more than 4, so I need to go to the right. And boom, I found 6. So let's write that method next. We're going to write the method to find our data. So we've got add. The next thing we're going to do is we're going to look for search. So we're going to say private. We could just, usually you've got more information in your binary tree, like you're looking for, like maybe the name of a student or something like that. Let's just return true or false if a certain item is in our binary tree. So I'm going to say Boolean. So private Boolean, let's just say contains int x. Okay. So first thing we need to do is we need to figure out, hey, is the tree empty, right? So if the root is null, that means we haven't added anything. Just return false. Okay, just return false. Obviously, there's nothing in our tree, right? Well, else, then we need to go searching. So we have a root now. So let's say node current is equal to our root. So our current now references our root, and we want to ask. We want to keep looping, but it turns out we might not have it. So if we ever get to a place where we're null, that means we haven't found it. So we're going to say while current does not equal null. We'll say if let's take a look at the diagram. How's this going to work, right? Let's say we were looking for the number, I don't know, like the number 6, and I'll put 6 right there. I'm done with this little tree. All right. Well, we're going to start with current pointing to our root. Okay. So current is right here. Current's going to start here, and we're going to ask. Well, we're looking for the number 6. Well, 6 is greater than 5, so we're going to set current to current.right. And we're going to say, hey, Are you the right thing? Are you 6? No, you're not 6. Okay. Well, 6 is less than you, so I'll set current to your left. Okay, are you 6? Yes, I am. Boom. Okay, I found it. Great. Return true. What if I was looking for the number 2? You'll notice 2 is not in this set, right? Well, again, we're going to start with our current pointing at the root. 2 is less than 5, so we'll make current point to its left child. 2 is less than 3, we'll make it point to its left child. 2 is greater than 1, so we'll make it point to its right child, which is null. So I need to get out of my loop and return false because I reached null. So that's how that's going to go. So if x is less than current.data, then we need to slide right. We'll say current is equal to current.left. Slide left, excuse me. Else, if x is greater than current.data, we need to slide right. Else, well, if you're not greater than, you're not less than, we must be equal to it, so we'll just return true. If we get to this point in the loop, that means we've the algorithm, we've exited the while loop and we never found it. And then we can return false. Okay, so that covers, and you should try that out, but that covers our basic adding and containing so that we can search. The runtime, because we're continuously splitting the tree in half, repeatedly dividing by 2, this has a runtime of O log n. So we're actually able to search in log n time. What about adding? Well, we're having the, we're basically searching when we add, but we're eliminating half the tree. So we're not getting O1 add, but we are able to add to anywhere in this tree in O log n time. Well, we will handle tree traversals in our next lesson and printing stuff out, and that's a really fun lesson. So practice adding and practice contains. Take care.